Most people imagine planets as places where life might exist, but the overwhelming majority of planets in the universe were never built for life at all. They were built for extremes. There is a confirmed planet where iron rises into the atmosphere, cools, and falls back to the surface as molten rain. There is another so dark that it reflects less light than fresh asphalt, swallowing almost everything that reaches it. One world is being torn apart by its own star, shedding part of itself into space with every orbit. Another is so hot that its surface reaches temperatures normally associated with small stars rather than planets. None of these are thought experiments. None of them are science fiction. Every one has been observed, cataloged, and published in peer reviewed scientific journals. They exist right now, orbiting real stars across our galaxy. For billions of years, the universe has been making planets. The unsettling truth is that worlds like Earth appear to be the exception, not the rule. Some discoveries have become so strange that astronomers have had to rethink how planets form, how they evolve, and even what should be possible under the laws of physics. By the time researchers realized how bizarre these worlds really were, the universe had already been building them for billions of years. Before we go any further, if you enjoy exploring the cosmos with us, a quick like or subscribe goes a long way. It helps us keep making these deep dives for curious minds like yours. Let's start with how we find other worlds. Long before telescopes reached beyond our own planetary neighborhood, people traced a handful of wandering lights across the night sky. Those moving points became the first known planets, companions to human imagination for thousands of years. Every other star remained a distant mystery. We could wonder about unseen worlds, yet no observation could prove they truly existed. That changed during the early 1990s. Astronomers studying a pulsar, the rapidly spinning remnant of an exploded star that sends regular beams of radiation across space, noticed tiny irregularities in its timing. Those minute changes revealed the gravitational pull of orbiting planets. The first confirmed worlds beyond our own solar system were found circling a stellar corpse. Few expected such a beginning, but another surprise soon followed. In the middle of the 1990s, researchers confirmed a giant planet orbiting the star known as 51 Pegasi. The planet circled astonishingly close to its parent star, far closer than Mercury circles our own sun. Existing theories struggled to explain how such a massive world could occupy that location. Planetary science suddenly had new questions to answer. Finding these distant worlds depends on remarkable precision. One of the most successful approaches is called the transit method, meaning a planet briefly passes across the face of its star from our point of view. During that crossing, the star grows ever so slightly dimmer. The change can be incredibly small, only 1/100th of 1%, yet modern instruments measure it with astonishing accuracy. The National Aeronautics and Space Administration launched the Kepler Space Telescope in the year 2009. During nearly a decade of observations, continuing until 2018, it monitored more than 150,000 stars at once. From those steady measurements came confirmation of more than 2,600 planets. A field built largely on expectation became one supported by extensive observation. Another observatory continued the search. The Transiting Exoplanet Survey satellite expanded the effort beyond one fixed region, scanning almost the entire sky for fresh planetary transits around nearby stars. Every successful detection strengthened an ever growing catalog, revealing systems with astonishing diversity. Today, the James Webb Space Telescope carries the investigation even further. As starlight filters through a planet's atmosphere during a transit, different gases absorb specific wavelengths of light. That unique pattern acts like a chemical fingerprint, allowing scientists to identify substances such as water vapor or carbon dioxide without ever visiting the world itself. The confirmed catalog now contains well over 5,600 planets as of the year 2024. Most bear little resemblance to Earth. Yet every remarkable discovery begins with the same patient practice, watching distant starlight fade by the smallest imaginable amount, then allowing physics to reveal an unseen world. Imagine standing before a weather forecast that predicts molten metal instead of clouds. That forecast belongs to a confirmed world known as WASP 76b, located about 640 light years away, which is about 376 quadrillion miles, in the constellation Pisces. Its remarkable atmosphere was studied in the year 2020 using the Echelle spectrograph for rocky exoplanets and stable spectroscopic observations mounted on the European Southern Observatory Very Large Telescope in Chile. Astronomers classify this planet as an ultra-hot Jupiter, meaning a giant gas planet orbiting extraordinarily close to its parent star. The immense pull of that nearby star has tidally locked the planet, a process where gravity synchronizes rotation with orbit until the same hemisphere always faces the star. One side remains under relentless daylight. The opposite hemisphere never receives direct starlight. Between them lies a narrow boundary where extraordinary chemistry unfolds. The day side reaches roughly 2,400 degrees Celsius or 4,352 degrees Fahrenheit. Those conditions are intense enough for iron to enter the atmosphere as vapor under the planet's unusual pressures. On Earth, we think of iron as something rigid and enduring. Here it behaves more like water rising from a warm ocean. Powerful global winds sweep that vapor away from the blazing hemisphere toward the colder side of the planet. But the night side is only cooler by comparison. Temperatures still exceed 1,000 degrees Celsius or 1,832 degrees Fahrenheit. Even so, that reduction allows the iron vapor to condense into liquid droplets. Across this distant sky, molten iron falls through the atmosphere as rainfall unlike anything found within our own solar system. Scientists uncovered evidence for this remarkable process near the terminator line, the narrow region separating perpetual daylight from everlasting darkness. They examined subtle shifts in the light arriving from the host star. This technique, called the Doppler effect, measures tiny changes in wavelength caused by motion toward or away from us. Iron absorption signatures appeared where researchers expected material to move between the two hemispheres, revealing a dynamic atmospheric circulation unlike any previously confirmed. One complete orbit lasts only about 1.8 Earth days. Each rapid circuit keeps the gravitational lock firmly in place, preventing any familiar pattern of sunrise or sunset. For countless ages, one hemisphere has remained exposed beneath relentless stellar energy, while the other has existed beneath an unchanging cosmic night. We often imagine weather as something shaped by water, clouds, and ice. WASP 76b expands that idea beyond recognition. Its atmosphere demonstrates that weather simply requires matter changing form, while energy and motion carry it across a world. In this astonishing environment, iron itself becomes part of a planetary climate, reminding us that nature follows physical laws with extraordinary creativity, even when the result seems almost beyond belief. From a great distance, you might mistake this world for a beautiful ocean planet. Its deep cobalt color feels strangely familiar, almost inviting. Yet that first impression dissolves as soon as we understand what our instruments are actually seeing. This confirmed exoplanet, known as Hotel Delta 189733b, lies about 64 light years away, which is about 376 trillion miles, within the constellation Vulpecula, completing one orbit around its star in only about 2.2 Earth days. Its remarkable blue appearance comes from silicate particles suspended high in the atmosphere. Silicates are minerals that include quartz and many common rocks found on Earth. Tiny grains of these minerals scatter blue wavelengths of starlight, producing a color that resembles our own planet from afar. But beneath that familiar shade waits an environment unlike anything experienced within our solar system. Average temperatures approach 1,000 degrees Celsius, or 1,832 degrees Fahrenheit. At those extraordinary temperatures, the atmosphere becomes a furnace of moving mineral particles. Winds race across the planet at nearly 8,700 kilometers per hour, which is about 5,406 miles per hour. That speed reaches roughly 7 times faster than the speed of sound through Earth's atmosphere. Those winds never truly rest. They drive countless microscopic fragments of heated silicate across the planet in an endless storm. Each particle is extremely small, yet the immense velocity transforms even tiny grains into dangerous projectiles. A grain comparable in size to ordinary sand can strike with energy similar to that of a rifle bullet. Nothing familiar could endure such conditions for more than an instant. But speed alone does not create this astonishing weather. Like the previous world we explored, this planet is tidally locked. One hemisphere remains directed toward its star, while the opposite hemisphere faces perpetual darkness. The enormous temperature contrast between those two sides powers a continuous atmospheric circulation, creating a planetary jet stream of exceptional strength that never weakens through changing seasons or daily cycles. This world also became a milestone in another way. During the year 2007, astronomers detected water vapor within its atmosphere, making it the first confirmed exoplanet where atmospheric water was identified. That discovery demonstrated that distant planetary atmospheres could be studied directly rather than imagined through theory alone. Water exists there, yet it shares the sky with blistering heat and storms of airborne rock. We often associate blue skies and water with places where life might flourish. Hotel Delta 189733B reminds us that familiar colors can conceal profoundly unfamiliar realities. Across this distant atmosphere, beauty and violence exist together, shaped only by gravity, chemistry, and relentless stellar energy. Some worlds challenge us through violence, others do so through possibility. The planet known as 55 Cancri E belongs to the second group, inviting us to imagine an interior unlike anything beneath our own feet. It orbits the star 55 Cancri A, about 41 light years away, which is about 241 trillion miles, within the constellation Cancer. This remarkable planet belongs to a class called a super-Earth, a rocky world, larger and more massive than Earth, while remaining much smaller than the giant planets. It measures roughly twice Earth's diameter and contains about 8 times Earth's mass. Its orbit is astonishingly brief. One complete journey around its star takes only about 17.7 hours, giving it a year that ends before a single Earth day has passed. Such proximity comes at an enormous cost. The hemisphere facing its star reaches temperatures near 2,400 degrees Celsius, or 4,352 degrees Fahrenheit. Those conditions are consistent with molten rock spread across much of the surface, perhaps forming vast seas of glowing lava that never have an opportunity to cool and solidify beneath the relentless stellar energy. But heat alone does not explain why this planet has fascinated astronomers for years. During the year 2012, researchers at Yale University examined the measured properties of the planet alongside the chemical composition of its parent star. They noticed an unusually high ratio of carbon compared with oxygen. That observation inspired an extraordinary proposal. Deep within the planet, immense pressure could compress carbon into enormous layers of diamond. On Earth, diamonds form when carbon experiences tremendous pressure and heat deep below the surface. The same physical process may occur here on an incomparably larger scale. Some models suggest that a diamond-rich interior could contain material totaling nearly 3 times the mass of Earth. We cannot observe those hidden layers directly. They remain a carefully constructed scientific hypothesis supported by measured stellar chemistry rather than direct exploration. But the surprises continued. Observations published during the year 2023 using the James Webb Space Telescope indicated the possible presence of a volatile atmosphere containing carbon dioxide or carbon monoxide. Either possibility was unexpected because intense radiation from the nearby star should gradually strip atmospheric gases into surrounding space. If such an atmosphere truly persists, it reveals that processes we do not yet fully understand continue to replenish or preserve it. 55 Cancri E has become a testing ground for entirely new ideas about rocky planets. Models built to explain Earth's silicate-rich interior cannot simply be expanded and applied here. Different ingredients produce different worlds. Its distance also reshapes our perspective. At the speed of Voyager 1, the fastest spacecraft humanity has launched, reaching this planet would require roughly 700,000 years. We can analyze its chemistry today, yet touching its surface remains far beyond our present reach. That contrast is part of its enduring wonder. That contrast is part of its enduring wonder. Brightness often makes distant worlds easier to understand. Reflected starlight reveals clouds, atmospheres, and changing surfaces. But one remarkable planet almost refuses to participate in that conversation. It hides within its own darkness. Known as TRES 2b, this confirmed exoplanet lies about 750 light-years away, which is about 441 quadrillion miles, and entered the scientific catalog after its discovery during the year 2006 through the Transatlantic Exoplanet Survey. Among all confirmed planets, this one holds an extraordinary distinction. It reflects less than 1% of the light reaching its atmosphere. To appreciate how unusual that is, consider familiar comparisons. Coal reflects roughly 4% of incoming light. Our moon reflects about 12%. Earth returns roughly 30% back into space through clouds, oceans, and ice. TRS-2b reflects almost nothing. Its appearance defies intuition. The planet is darker than black paint, developed for ordinary applications, and darker than any naturally occurring surface measured on Earth. If you somehow approached this giant world, it would not stand out as a bright sphere against surrounding space. Instead, it would resemble an almost invisible shape with only the faintest hint of its true presence. But scientists still cannot fully explain why. That uncertainty has become one of the planet's most fascinating characteristics. Current research suggests its atmosphere may contain vaporized sodium, potassium, and titanium oxide. These substances absorb visible light with remarkable efficiency, preventing much of the incoming starlight from escaping back into space. Even after years of atmospheric modeling, No single explanation completely accounts for the extraordinary darkness observed. This mysterious world belongs to the family of hot Jupiters, giant gas planets orbiting extremely close to their parent stars. TRES, 2b circles, at only about 1/50th of Mercury's orbital distance from our Sunday. Such proximity raises its dayside temperature to around 1000 degrees Celsius or 1832 degrees Fahrenheit. Although the atmosphere swallows nearly every ray of visible light, the accumulated heat cannot remain trapped forever. Every warm object radiates energy. That physical law applies here as well. Heated to such extraordinary temperatures, the planet emits its own faint thermal glow, appearing as a dim reddish ember rather than a completely invisible body. Its glow does not come from reflected starlight. It comes from the planet itself, slowly releasing absorbed energy back into space. If you viewed TRES 2b with your own eyes from nearby, detecting it would remain extraordinarily difficult despite its immense size. Against the surrounding darkness, only a weak crimson shimmer would betray its existence. We often assume that measuring reflected light should reveal a world's nature with relative ease. TRES 2b reminds us that the universe still guards many of its deepest secrets, allowing an entire planet to absorb almost everything that reaches it, while revealing only the faintest trace of its own enduring heat. When we hear the word cloud, we instinctively picture drifting water droplets carried by familiar winds. That expectation works well on Earth. It fails completely on the distant world called Kepler 7b. Here, the sky follows the same physical principles, yet the material moving through those principles belongs to an entirely different category of matter. Kepler 7b is a confirmed hot Jupiter located about 1,000 light-years away, that is nearly 588 quadrillion miles. It was discovered during the year 2010 by the Kepler Space Telescope. Although larger than Jupiter, the planet contains only about half as much mass. That unusual combination makes it one of the least dense planets ever confirmed, with an average density comparable to expanded polystyrene foam. Its atmosphere soon revealed another surprise. During the year 2013, the National Aeronautics and Space Administration announced the first successful map of cloud cover on an exoplanet. Scientists combined thermal measurements gathered by the Spitzer Space Telescope with visible light observations collected by the Kepler Space Telescope. By comparing how different regions reflected and emitted light, they reconstructed the distribution of clouds across the planet. But these clouds are nothing like those drifting above Earth's oceans. They consist primarily of silicates, a family of minerals that includes glass and many common rocks. At the extraordinary temperatures found high in this atmosphere, those minerals can exist as microscopic suspended particles, creating vast cloud systems composed of vaporized rock rather than water. Even more remarkable, the clouds are unevenly distributed. They gather mainly across the western portion of the permanent dayside, instead of spreading evenly around the globe. That imbalance changes how much starlight different regions reflect. Careful observations detected this subtle difference, allowing astronomers to identify where the densest cloud formations were located without ever seeing the planet directly. The explanation depends upon familiar physics operating with unfamiliar materials. On Earth, water evaporates, rises, cools, condenses, and forms clouds before returning as precipitation. Kepler 7b follows a similar sequence. Rock evaporates within the hotter eastern regions of the dayside. Atmospheric circulation then transports that mineral vapor westward. As temperatures decline slightly, The material condenses into suspended silicate particles, building enormous cloud banks that remain aloft. We usually connect weather with rain, snow, and oceans. Kepler 7b broadens that definition dramatically. Weather is simply the movement of matter through changing temperatures and pressures. Water happens to shape Earth's atmosphere. Elsewhere, iron, silicates, and other minerals can perform the same role under different conditions. Above this remarkable world stretches a sky filled with clouds. They drift, gather, and evolve according to the same universal laws that shape weather on Earth. Only the substance has changed, transforming an ordinary meteorological process into one of the most extraordinary atmospheres yet discovered. History sometimes begins in the least expected place. The first confirmed planets beyond our own solar system were never discovered around a warm, familiar star. Instead, they emerged from observations of something far stranger, the collapsed core of a star that had already destroyed itself in a tremendous supernova explosion long before those planets were detected. This remarkable object is known as Pulsar B 1257 plus 12. It lies about 2,300 light years away, that is nearly 1,352 quadrillion miles, within the constellation Virgo. It belongs to a class called a millisecond pulsar, meaning a compact stellar remnant that spins hundreds of times every minute while sweeping beams of electromagnetic radiation through space with astonishing regularity. The pulsar completes about 161 rotations every second. Each sweep arrives with extraordinary precision, allowing astronomers to measure even the smallest irregularities in its rhythm. During the year 1992, Alexander Wolszczan and Dale Frail noticed tiny variations in those otherwise dependable pulses. Those changes revealed the subtle gravitational influence of unseen companions circling the pulsar. Their discovery transformed astronomy. 3 planets were eventually confirmed. 2 possess masses broadly comparable to Earth's and orbit, at distances similar to Mercury's position around our Sunday. A third, smaller world travels along an even closer path. None of them should have existed, according to earlier expectations. The parent star had already exploded, scattering enormous quantities of material across surrounding space. But gravity rarely wastes available matter. Astronomers believe the supernova debris gradually settled into a rotating disk around the pulsar. Over time, countless fragments collided, merged, and accumulated into entirely new planetary bodies. In this extraordinary setting, destruction became the foundation for another cycle of planetary formation. The surrounding environment remains extraordinarily hostile. A millisecond pulsar floods nearby space with intense beams of high-energy radiation and streams of energetic particles. The amount of radiation reaching these planets exceeds what Earth receives from the Sun by millions of times. Under such conditions, familiar biological chemistry cannot survive for long. Atmospheres would struggle to remain intact, while exposed surfaces endure relentless bombardment from powerful radiation. But the importance of these planets has never depended upon their ability to support life. Their existence demonstrated something even more profound. Planet formation is not limited to peaceful neighborhoods surrounding stable stars. Whenever gravity gathers enough material into orbit, nature appears willing to build worlds, even around the remains of stellar catastrophe. Before the year 1992, confirmed exoplanets belonged only to speculation. After this discovery, the conversation changed forever. Astronomers no longer debated whether planets existed beyond our solar system. They began asking what astonishing forms those distant worlds might take. With every new observation since then, the universe has answered that question with possibilities far more diverse than anyone had imagined only a generation earlier. For almost every planet we have explored so far, a star has served as the center of its story. Gravity bound each world to a dependable source of light and heat. But the galaxy also contains planets that belong to no star at all. They travel alone, crossing the vast spaces between stellar systems with no sunrise, no familiar sky, and no destination waiting ahead. Astronomers call these objects rogue planets, sometimes also known as free-floating planets. Most likely, they formed within ordinary planetary systems before violent gravitational encounters changed their fate. During the chaotic early stages of planetary formation, close interactions with giant planets could hurl smaller worlds completely out of their native systems. Once enough speed was gained, gravity released them forever into interstellar space. Finding such lonely travelers presents an enormous challenge. They reflect almost no light because no nearby star illuminates them. Instead, astronomers rely upon a technique called gravitational microlensing. This phenomenon occurs when the gravity of a passing object bends and briefly magnifies the light from a much more distant background star. The temporary brightening reveals the otherwise invisible planet moving across our line of sight. But these opportunities are fleeting. They may occur only once for any particular rogue planet. Even so, observations continue to improve. During the year 2023, researchers analyzing data gathered by the Kepler Space Telescope identified about 70 candidate rogue planets toward the galactic bulge, the densely populated central region of the Milky Way. Some theoretical models now suggest that planets wandering freely through the galaxy could actually outnumber the stars themselves. The conditions upon these isolated worlds depend greatly on their size. Small, rocky planets gradually lose their remaining heat across billions of years. Eventually, their surfaces approach roughly negative 270 degrees Celsius, or negative 454 degrees Fahrenheit, only a few degrees above absolute zero, the lowest temperature physically possible, where molecular motion nearly ceases. Larger worlds tell a different story. Massive gas giants continue generating internal warmth through gravitational compression, the process in which enormous pressure slowly converts gravitational energy into heat deep within the planet. That heat may persist for astonishing lengths of time. Beneath thick hydrogen atmospheres, subsurface oceans of liquid water could remain stable even without any nearby star providing external warmth. This possibility rests upon established physical principles rather than imagination. One well-studied candidate, known as Canada-France Brown Dwarfs Survey Infrared 2149-0403, was identified during the year 2012. Estimated to contain between 4 and 7 times Jupiter's mass, it lies about 100 light-years away, which is about 588 trillion miles, drifting through interstellar space, completely alone. We often think of planets as faithful companions to stars. Rogue planets reveal another path entirely, where gravity sends entire worlds into endless journeys across the darkness, carrying only the fading warmth locked inside their own deep interiors. Sometimes the greatest discoveries do not answer old questions. They erase them completely. That is exactly what happened when astronomers confirmed the existence of 51 Pegasi b during the year 1995. Here was a giant planet circling its star much closer than Mercury circles our own Sunday. According to every accepted model at the time, such a world should never have formed. Planetary formation theory had seemed comfortably established. Giant planets were expected to grow only in the cold outer regions surrounding young stars. There, substances such as water ice, methane ice, and ammonia ice could remain frozen. These solid materials gradually collected into massive cores. Once those cores became large enough, gravity pulled in enormous quantities of surrounding gas, eventually creating worlds similar to Jupiter and Saturn. But the inner regions around a young star are far hotter. Ice cannot survive there. Without frozen material, researchers believed no sufficiently large core could ever develop. The ingredients simply appeared to be missing. Yet 51 Pegasi b existed anyway, moving around its star in only a few days and forcing planetary scientists to reconsider assumptions that had seemed remarkably secure. The solution emerged through a process now known as planetary migration. This idea proposes that giant planets still begin their lives far from their stars, exactly where theory predicted. Their journey changes afterward. While embedded within the broad disk of gas and dust surrounding a young star, the growing planet exchanges angular momentum, meaning the quantity that describes orbital motion, with the surrounding material. As this exchange continues across millions of years, the planet gradually loses orbital energy and spirals inward until the disk disperses or a stable orbital arrangement halts its movement. But such migration carries dramatic consequences for every smaller world already occupying the inner system. Imagine an object carrying roughly Jupiter's mass, steadily crossing the orbits of young rocky planets. Some worlds would be thrown into distant space, others would plunge into their parent star. Still others could collide with neighboring planets, leaving behind shattered debris rather than stable planetary families. Because of this destructive journey, astronomers believe hot Jupiter systems are statistically unlikely to contain habitable rocky planets close to their stars. The giant planet would probably have cleared that region long before life had any opportunity to begin. Each migrating giant reshapes its entire planetary neighborhood. Even so, hot Jupiters remain relatively uncommon. Surveys indicate they appear around roughly 1% of known stellar systems. That fraction sounds modest, but when you remember the Milky Way contains hundreds of billions of stars, the number expands into hundreds of millions of planetary systems dominated by these scorching giants. Our own solar system appears to have followed a different path. Jupiter remained in the distant outer regions, allowing the inner rocky planets to survive and continue evolving. But whether that outcome represents ordinary cosmic history or an unusually fortunate exception remains one of planetary science's most compelling unanswered questions. Perspective changes everything. As our catalog of distant worlds expanded, astronomers gradually realized that the planets surrounding our own sun may not represent the galactic standard at all. The worlds most frequently discovered across the Milky Way belong to categories completely absent from our neighborhood. We have searched our own planetary family repeatedly, yet nothing occupies the broad middle ground between Earth and Neptune. Earth provides the familiar starting point. Neptune measures nearly 4 times Earth's radius. Between those two sizes lies an entire population of planets appearing again and again around distant stars. Some are called super-Earths, meaning enlarged rocky planets. Others are known as mini-Neptunes, worlds wrapped in thick envelopes of hydrogen and helium. Their outward appearance may seem similar, but their internal structures can be profoundly different. The distinction depends largely upon density. Density tells astronomers how much matter occupies a given volume, offering valuable clues about what lies beneath the clouds. A dense planet, likely contains extensive layers of rock and iron. A lower density suggests enormous quantities of light gases surrounding a comparatively modest rocky core. Measuring that density requires combining observations of a planet's size with careful measurements of its mass, allowing researchers to estimate the materials hidden from direct view. But increasing a rocky planet's size changes more than its appearance. Gravity grows stronger as mass increases. A large super Earth with an iron core and rocky mantle resembling Earth's could produce surface gravity roughly 2 or 3 times stronger than what you experience here. Your body would remain unchanged, yet every movement would demand greater effort as your weight increased dramatically beneath the planet's relentless pull. The atmosphere might become equally formidable. On some super Earths, surface pressures could reach dozens or even hundreds of times greater than Earth's atmospheric pressure. Those conditions resemble the crushing environments found many kilometers beneath Earth's oceans, where only specially designed equipment can endure the immense force pressing inward from every direction. Mini Neptunes present an even stranger picture. Instead of offering a solid landscape beneath open skies, these planets may possess no accessible surface whatsoever. Their thick hydrogen and helium atmospheres become progressively denser with depth until the gas slowly transforms into an intensely compressed fluid. There is no obvious shoreline between sky and interior. One state simply blends into another. Astronomers have also uncovered an intriguing statistical pattern called the Fulton Gap, sometimes known as the radius gap. Planets measuring between roughly 1.5 and 2 Earth radii appear surprisingly uncommon. Current evidence suggests many young planets either lose their gaseous envelopes entirely, becoming super Earths, or retain those envelopes and mature into mini Neptunes, leaving relatively few worlds occupying the space between. But perhaps the greatest surprise comes from looking homeward. Our solar system contains neither category. The reason remains uncertain. Current formation models have yet to explain why our planetary arrangement differs so markedly from the configurations appearing across much of the galaxy. As more distant worlds emerge from observation, we increasingly find ourselves living inside what may be one of the less typical planetary families after all. Imagine standing beneath a sky that never changes. The star above remains fixed in exactly the same place every moment of every year. Shadows never drift. Dawn never arrives. Evening never follows. On many of the worlds astronomers have discovered, this strange rhythm is not imagination at all. It is the natural outcome of a process called tidal locking. Tidal locking occurs when a planet circles close enough to its parent star that gravity gradually slows its rotation. Over immense stretches of time, the planet's spin becomes synchronized with its orbit. One complete rotation takes exactly as long as one complete trip around the star. As a result, the same hemisphere always faces the light, while the opposite hemisphere always faces deep space. We already know this phenomenon from much closer to home. Earth's moon is tidally locked, which is why you always see the same lunar face from our planet. Around distant stars, the same physical process operates on entire planets. The only difference is the object exerting the gravitational pull. But conditions become far more extreme when the locked body circles close to its star. One hemisphere receives uninterrupted stellar energy without pause. Surface temperatures on the illuminated side of a rocky planet may climb to around 1,000 degrees Celsius or 1,832 degrees Fahrenheit, depending upon the star's brightness and the planet's orbital distance. Across the opposite hemisphere, the absence of direct starlight allows temperatures to plunge toward roughly negative 100 degrees Celsius, or negative 148 degrees Fahrenheit, or even lower. That enormous temperature contrast transforms the atmosphere into a restless engine. Heated gases expand above the blazing hemisphere and surge toward the frozen hemisphere, while colder air returns in the opposite direction. But these circulating flows can become extraordinarily powerful, with winds reaching hundreds or even thousands of kilometers per hour, which is about hundreds or roughly 621 miles per hour, depending upon the planet's atmospheric properties and the strength of the temperature difference. Another challenge emerges as the cold side grows colder. Atmospheric gases may eventually freeze from the air itself, settling onto the surface as frost or ice. This process, called atmospheric collapse, gradually removes gases from circulation. If enough of the atmosphere becomes trapped on the frozen hemisphere, the planet's climate can change dramatically, leaving progressively less air available to transport warmth back across the globe. Yet these worlds may not be entirely inhospitable, but climate simulations suggest that a sufficiently thick atmosphere could carry enough heat from the illuminated hemisphere to prevent complete freezing elsewhere. Between the burning day side and the frozen night side lies the terminator region, meaning the boundary separating perpetual daylight from perpetual darkness. Under favorable conditions, this narrow ring may experience temperatures suitable for liquid water. This possibility has drawn particular attention to the 7 planets orbiting the star known as TRAPPIST-1. Researchers believe each of these worlds is tidally locked. Their long-term habitability depends greatly upon whether their atmospheres can efficiently redistribute heat across the globe. If they can, life might persist beneath a sky where the star never rises, never sets, and the horizon remains unchanged through countless ages. Some planets vanish in sudden catastrophe. Others fade through slow transformation across unimaginable ages, but a few allow us to witness destruction while it is already unfolding. WASP 12b belongs to that rare group, even across the vast distance separating us. Its gradual demise has become measurable, revealing a world losing itself to the relentless pull of the very star it orbits. This giant planet circles approximately 1,400 light years from Earth. It travels around its parent star at a distance of roughly 3.4 million kilometers, which is about 2.1 million miles. By comparison, Mercury remains about 57.9 million kilometers from our Sun, which is about 36 million miles. WASP 12b circles nearly 16 times closer to its star than Mercury does to ours, placing it deep inside an environment dominated by overwhelming gravitational forces. But gravity does more than keep the planet in orbit. The star's pull stretches the giant world continuously. Instead of remaining nearly spherical like Jupiter, WASP 12b has become elongated, assuming an egg-shaped form, with one side pulled toward the star while the opposite side stretches away. The deformation is not temporary. It has become part of the planet's very structure. The consequences extend beyond its shape. The upper atmosphere has expanded so far that the star's gravity steadily captures part of it. Gas escapes from the planet and flows outward, creating what astronomers call an accretion stream, meaning a continuous transfer of material from one object to another under the influence of gravity. This stream spirals toward the star, feeding it with matter that once belonged to the planet itself. Every orbit continues the process. WASP 12b circles its star in only about one Earth day. During each revolution, tidal interactions remove a tiny amount of orbital energy. The orbit gradually shrinks, drawing the planet incrementally closer. The closer it moves, the stronger the tidal forces become. But stronger tides accelerate the loss of material, creating a cycle that slowly hastens the world's destruction. Current estimates suggest the planet could disappear entirely within roughly 10 million years. Against the age of stars, that span represents only a brief chapter. A Jupiter-sized world is being dismantled before our instruments, losing the equivalent of about one Jupiter mass across that interval as its atmosphere steadily escapes into its parent star. What makes this discovery especially remarkable is our timing. We are observing WASP 12b during a narrow window in its history. The planet remains intact enough to retain its identity, yet its decay has advanced far enough for astronomers to detect changes in both its atmosphere and its orbit. We have arrived while the process is still unfolding. But the broader lesson reaches beyond a single planet. Hot Jupiters occupy unstable neighborhoods where immense gravitational forces reshape their futures. Worlds are assembled from swirling disks of gas and dust, yet those same cosmic laws can eventually pull them apart again. WASP 12b reminds us that planetary systems evolve without pause, and sometimes we are fortunate enough to witness one of those transformations as it happens. Long after the explosion has faded from view, the remains of a massive star continue shaping everything nearby. We have already encountered one remarkable pulsar system. Now we move closer to understand what it truly means to exist beside an object that compresses extraordinary mass into astonishingly little space, then floods its surroundings with relentless energy. A millisecond pulsar begins as the collapsed core left behind after a supernova. The original star tears itself apart, while its central region falls inward under overwhelming gravity until it forms a sphere only about 20 kilometers across, which is about 12.4 miles. Despite that modest diameter, the remnant contains more mass than our own Sunday. Matter inside has been squeezed into neutron star material, meaning atoms have collapsed so completely that ordinary structure no longer survives. Its density stretches beyond everyday experience. A single teaspoon of this material would weigh roughly 10 million tons if somehow transported intact to Earth. Nothing built by human engineering approaches such compression. The object itself remains remarkably stable, rotating tens or even hundreds of times every second, while powerful magnetic fields channel beams of electromagnetic radiation outward from its magnetic poles. Those beams sweep through space with astonishing regularity. Each rotation produces pulses so dependable that astronomers compare their timing to the precision of an atomic clock. But the dependable rhythm conceals an environment of extraordinary violence. The radiation consists of radio waves, X-rays, and gamma rays, all streaming outward with enormous energy. Any nearby planet repeatedly passes through those beams as the pulsar spins. For the planets orbiting the pulsar known as Papa Sierra Romeo Bravo 1257 plus 12, estimates suggest radiation exposure reaches between 100,000 and 1 million times the solar radiation Earth receives from the Sunday. You are not standing beneath warm daylight. Instead, high-energy beams sweep across the surface dozens of times every second, carrying particles capable of tearing apart molecules and damaging matter at the smallest scales. But radiation alone does not define these worlds. The pulsar also drives an intense particle wind, meaning a continuous outflow of energetic particles racing away from the collapsed star. Over immense spans of time, that bombardment strips away atmospheres that might once have surrounded nearby planets. Water disappears. Other volatile compounds, substances that evaporate easily under changing conditions, are driven into space or broken apart until little remains. The exposed surface endures an endless barrage resembling a planet-wide X-ray machine operating without interruption across billions of years. There is no familiar weather, no protective sky, and no ocean softening the impact of relentless energy. Only rock, mineral, and radiation remain locked together beneath the spinning beacon of a stellar remnant. Yet, these were the first confirmed planets discovered beyond our solar system. Their existence transformed astronomy forever. They proved that worlds can survive, or perhaps form anew, around the shattered corpse of a star. They continue their orbits with unwavering persistence, stripped, irradiated, and airless, tracing ancient paths around the object that once destroyed nearly everything in its reach. Long before any familiar world settles into a dependable orbit, every planetary system begins as a place of constant upheaval. When we observe distant systems today, we are seeing the survivors of ancient events whose most turbulent chapters ended long ago. The graceful arrangements we measure across the galaxy are the lasting records of countless collisions, migrations, and gravitational struggles that unfolded over hundreds of millions of years. The story begins inside a vast molecular cloud, a cold region filled with gas and dust drifting between the stars. Gravity slowly gathers that material inward. As the cloud contracts, pressure rises and temperatures climb until nuclear fusion begins within the growing star. Nuclear fusion is the process in which light atomic nuclei combine into heavier ones, releasing enormous amounts of energy. Around the newborn star, the remaining gas and dust flatten into a rotating protoplanetary disk, providing the raw material from which every future planet emerges. But nothing forms all at once. Accretion, the gradual growth of larger bodies through repeated collisions and sticking, transforms tiny dust grains into pebbles, pebbles into rocky fragments, fragments into planetesimals, and planetesimals into planetary embryos. These embryos, each large enough to exert substantial gravity, travel along unstable paths that frequently cross one another. Some merge, others shatter. Many are scattered into entirely different regions of the system. Those encounters reshape everything. Gravitational resonances, meaning repeated gravitational interactions that steadily alter orbital motion, can stretch once circular paths into elongated ones. Close approaches become increasingly common. Entire populations of young worlds disappear through collisions or ejection into interstellar space. What seems destructive also drives construction, because every merger creates larger and more stable planetary bodies. Our own history preserves evidence of this process. About 4.5 billion years ago, a planetary embryo called Theia is believed to have struck the young Earth. The impact partially vaporized both worlds, launching enormous amounts of material into orbit. Over time, that debris gathered together through gravity and formed the Moon, giving our planet a companion that continues shaping tides and stabilizing Earth's rotation. But the giant planets also transformed the developing solar system. Jupiter and Saturn likely exchanged gravitational influence while surrounded by the remaining disk. According to the Grand Tack hypothesis, Jupiter migrated inward until it reached roughly the present orbit of Mars before Saturn altered the balance, pulling Jupiter outward again. That remarkable migration redistributed enormous amounts of material, influenced the formation of the terrestrial planets, destabilized the asteroid belt, and likely contributed to the intense bombardment that scarred the young inner solar system about 3.9 billion years ago. The worlds we recognize today endured because they survived this prolonged era of elimination. Many neighboring bodies vanished through impact, capture, or expulsion. Others never completed their growth. But the planets that remained gradually settled into long lived orbits. What appears orderly beneath today's night sky is the enduring aftermath of extraordinary turmoil. Every mature planetary system carries the memory of ancient violence, and every world we discover is, above all else, a survivor. Sometimes, the strangest destination requires almost no journey at all. Before thousands of distant exoplanets transformed our understanding of the universe, the most formidable planetary environment known to science circled the very same star that gives life to Earth. At its closest approach, Venus comes within about 41 million kilometers, which is about 25.5 million miles, making this astonishing world our near neighbor rather than a remote curiosity. From afar, the resemblance is remarkable. Venus measures about 95% of Earth's diameter and holds roughly 81% of Earth's mass. Its gravity feels broadly familiar, and its rocky composition places it firmly among the terrestrial planets. Looking only at its size, you might expect another version of Earth, shaped by similar beginnings, beneath the same young Sunday. But appearances conceal an entirely different reality. The surface reaches approximately 465 degrees Celsius, or 869 degrees Fahrenheit, remaining astonishingly consistent across the planet. The equator and the poles experience nearly the same temperature. Day and night offer almost no relief. Mercury travels much closer to the sun. Yet Venus is even hotter because its atmosphere traps heat with extraordinary efficiency. That atmosphere is dominated by carbon dioxide, making up about 96.5% of its composition. The result is a runaway greenhouse effect, a process in which trapped heat continually intensifies because escaping thermal energy is blocked. Surface pressure climbs to roughly 92 times that experienced on Earth. Standing there would resemble being almost 900 meters beneath Earth's oceans, which is about 2,953 feet, except surrounded by crushing heat instead of cool seawater. But pressure and temperature tell only part of the story. High above the surface drifts a continuous global blanket of sulfuric acid clouds extending from roughly 45 kilometers, which is about 28 miles, to 70 kilometers, which is about 43.5 miles, above the ground. These are not scattered patches. They wrap around the entire planet, reflecting sunlight, while concealing the hostile landscape below. Human technology has briefly touched that landscape. The Soviet Union's Venera landers descended successfully through the atmosphere, transmitting invaluable data after landing. Yet each machine endured only between about 23 minutes and 127 minutes before the relentless conditions overwhelmed every system. Even our strongest spacecraft could borrow only a little time. Venus also turns differently from nearly every other planet. Its rotation is backward compared with Earth, causing the sun to rise in the west and set in the east. The rotation proceeds so slowly that one Venusian day lasts about 243 Earth days, while a complete orbit around the sun requires only about 225 Earth days. But evidence increasingly suggests this inferno may once have supported liquid water across its surface. Some climate models indicate habitable conditions could have persisted for as long as 2 billion years before powerful feedback processes transformed the planet. Scientists suspect widespread volcanic activity, including a massive resurfacing episode between roughly 500 million and 700 million years ago, released enormous quantities of carbon dioxide that accelerated the runaway greenhouse effect. Venus reminds us that familiar beginnings do not guarantee familiar destinies, and worlds that once resembled Earth can follow profoundly different paths. Long before we could ever visit another world, we learned to read the faint traces drifting above it. As a distant planet passes across the face of its star, a small fraction of starlight filters through the planet's atmosphere before continuing toward us. That altered light carries subtle clues, allowing the James Webb Space Telescope to perform transmission spectroscopy, a technique that reveals atmospheric chemistry by measuring how different wavelengths are absorbed during a planetary transit. Each molecule leaves its own unmistakable signature. Water absorbs particular portions of infrared light. Carbon dioxide blocks others. Methane creates a different pattern altogether. These tiny changes become spectral fingerprints, unique arrangements that let astronomers identify substances far beyond our own solar system without ever touching the worlds where they exist. But those fingerprints often describe environments unlike anything surrounding the planets we know best. One remarkable example arrived in 2022 when the James Webb Space Telescope detected carbon dioxide in the atmosphere of WASP 39b. It marked the first unambiguous detection of carbon dioxide within the atmosphere of an exoplanet, demonstrating that distant planetary chemistry could finally be measured with extraordinary confidence rather than inferred through indirect evidence. The same observations uncovered sulfur dioxide high above that planet. On Earth, sulfur dioxide commonly appears through volcanic eruptions or industrial activity. Around WASP 39b, the story unfolds very differently. Intense stellar radiation triggers photochemical reactions, meaning sunlight itself drives chemical transformations that continually manufacture sulfur dioxide within the atmosphere. The laws of chemistry remain unchanged, yet the surrounding conditions produce entirely unfamiliar outcomes. Temperature, pressure, and radiation reshape matter in remarkable ways. Some intensely heated giant planets contain titanium oxide, suspended as a gas rather than locked inside minerals. On Earth, this compound is widely recognized as a bright white pigment found in paints and coatings. Under atmospheric temperatures approaching 2000 degrees Celsius or 3632 degrees Fahrenheit, titanium oxide absorbs incoming stellar energy so efficiently that the upper atmosphere becomes hotter than the layers below. This reversal, known as a temperature inversion, is the opposite of the pattern found in Earth's lower atmosphere. But even these remarkable worlds are surpassed by Kelt 9b. Its dayside reaches roughly 4,300 degrees Celsius, or 7,772 degrees Fahrenheit, exceeding the surface temperatures of many small stars. Under such relentless heat, familiar molecules, including water, methane, and carbon dioxide, cannot remain intact. Their chemical bonds are torn apart before stable structures can persist. Instead, atoms of iron and titanium drift through the atmosphere as gases. Materials that usually form solid metal or rock become part of the air itself. You are looking at a planet whose atmospheric composition resembles conditions normally associated with stellar surfaces rather than planetary skies. Across the galaxy, chemistry follows universal physical laws, yet it assembles astonishingly different worlds whenever those laws are given unfamiliar environments in which to unfold. Imagine looking upward and finding that daylight comes from more than one direction. Across the Milky Way, this is not an extraordinary exception. Roughly half of all stellar systems contain two or more stars bound together by gravity, circling one another through cycles that can last from days to centuries. For many years, Astronomers doubted whether stable planetary systems could emerge within such constantly shifting gravitational landscapes. The concern appeared reasonable. A young planet developing around one star would continually feel the pull of another nearby star, altering its orbit over immense spans of time. Those repeated gravitational disturbances, meaning gradual changes caused by competing forces, seemed likely to scatter planets into deep space or send them crashing into one of their parent stars. Planet formation around binary stars appeared fragile from the beginning, but the universe once again proved more inventive than our early theories. In 2011, astronomers confirmed Kepler 16b, the first known circumbinary planet, meaning a planet that circles both stars instead of orbiting only one. This gas giant is similar in size to Saturn and travels around a pair of stars, one possessing about 69% of the Sun's mass and the other about 20%. A complete orbit requires about 229 Earth days. Although Kepler 16b itself is a gas giant, you can imagine standing upon a large moon circling that distant world. Two suns would climb above the horizon instead of one. The brighter primary star would dominate the sky, while its smaller companion followed a different path. Sunrise and sunset would rarely occur together. Shadows would stretch in separate directions before merging and separating again as each star moved across the heavens. Kepler continued searching, and more examples followed. At least a dozen circumbinary planets have now been confirmed, demonstrating that planets can assemble successfully even while two stars continually reshape the surrounding gravitational environment. Rather than preventing planetary birth, many binary systems appear capable of guiding disks of gas and dust into surprisingly durable arrangements that endure for billions of years. But circumbinary worlds represent only one possibility. Some planets follow circumstellar orbits, remaining tightly bound to a single star, while a second star circles much farther away. In these systems, the distant companion slowly perturbs planetary paths through repeated gravitational influence. Over immense timescales, those subtle effects may stretch or tilt orbits, alter planetary climates, or occasionally drive entire systems toward instability. Computer simulations continue exploring where the boundary between stability and chaos truly lies. Some closely paired stars support planetary systems that remain remarkably consistent across billions of years. Others gradually unravel through countless small gravitational exchanges. We have learned that two suns do not automatically prevent worlds from surviving. Instead, they reveal another architectural design written into the universe, where daylight can arrive from separate stars and familiar ideas of a planetary sky expand far beyond anything once imagined. The search has become increasingly focused. After discovering that planets exist in astonishing variety, astronomers now ask a more demanding question. Which rocky worlds still possess an atmosphere capable of enduring across billions of years? Every new observation from the James Webb Space Telescope brings us closer to an answer, even when that answer proves less encouraging than many hoped. For small planets orbiting near their stars, survival is never guaranteed. A continuous flow of charged particles, known as stellar wind, streams outward from every star. Over immense stretches of time, that relentless flow can erode a planet's atmosphere by carrying lighter gases away into space. Gravity alone is sometimes insufficient to hold everything in place when the bombardment continues for billions of years. Earth has an important advantage. Deep beneath our feet, a rotating molten iron core generates a magnetic field, an invisible protective region that deflects much of the incoming solar wind before it reaches the upper atmosphere. That shielding has helped preserve the air surrounding our planet through vast spans of geological history. But when we study distant rocky planets, determining whether they possess similar magnetic protection remains beyond the reach of present instruments. Scientists must instead rely on indirect evidence, and those conclusions remain uncertain. But observations are steadily improving. One major milestone arrived in March of 2023 when the James Webb Space Telescope measured the thermal emission of TRAPPIST 1b, the innermost member of a remarkable family of 7 rocky planets orbiting a cool red dwarf star about 40 light years away. Thermal emission simply means the heat radiated naturally from a planet itself, allowing astronomers to estimate its surface conditions. The measurements suggested a sobering picture. The dayside temperature reached roughly 230 degrees Celsius or 446 degrees Fahrenheit, matching what researchers expected from an exposed rocky surface with little or no atmosphere available to transport heat toward the opposite hemisphere. Instead of circulating warmth, the planet appears to leave one side facing the full intensity of its star. Similar evidence emerged from observations of TRAPPIST 1c. Those results also failed to reveal a thick carbon dioxide atmosphere surrounding the planet. But farther outward, TRAPPIST 1e, TRAPPIST 1f, and TRAPPIST 1g still occupy the habitable zone, the orbital region where temperatures could allow liquid water to exist if suitable atmospheric conditions are present. Their atmospheres, however, remain largely unmeasured. Another challenge complicates the picture. Red dwarf stars spend their youth in a far more energetic state than they display later in life. During those early stages, they produce stronger radiation and more powerful stellar winds, conditions capable of stripping atmospheres from nearby planets before those worlds have time to settle into lasting stability. Each new measurement returned by the James Webb Space Telescope narrows the possibilities. But so far, the growing evidence suggests that retaining an atmosphere around small, rocky planets may be more difficult than astronomers once imagined. Our attention often settles first upon the largest object in a planetary system. Yet some of the most compelling destinations are much smaller companions circling giant worlds. Here in our own solar system, the strongest candidates for environments that might support life are not planets at all. They are moons, shaped by forces that operate far beneath frozen surfaces. Europa, one of Jupiter's largest moons, hides a global ocean beneath an icy shell estimated to be between 10 kilometers, which is about 6.2 miles, and 30 kilometers, that is nearly 19 miles, thick. Although sunlight barely warms its surface, the ocean remains liquid because of tidal heating. As Europa travels through Jupiter's immense gravitational field, the moon is repeatedly stretched and compressed. That continual flexing generates internal heat, preventing the hidden ocean from freezing solid. Another remarkable example circles Saturn. Enceladus measures only about 504 kilometers across, which is about 313 miles. Yet beneath its bright icy crust lies another global ocean. Near its south pole, towering geysers erupt through fractures in the surface, launching water into space. The Cassini spacecraft flew directly through those plumes and detected water, organic molecules, molecular hydrogen, and tiny silica particles. Together, these discoveries strongly suggest hydrothermal activity, where heated water interacts with rock on the ocean floor. But Saturn offers an entirely different surprise as well. Titan possesses a dense atmosphere dominated by nitrogen, thicker than Earth's in many respects. Across its landscape lie lakes, rivers, clouds, and rainfall. The difference is the liquid itself. Instead of water, Titan's weather cycle is built from liquid methane and ethane, demonstrating that familiar geological processes can continue even when the chemistry changes dramatically. Jupiter's moon Io reveals another consequence of tidal heating. It is the most volcanically active body in our solar system. Hundreds of volcanoes continually reshape its surface, while enormous sulfur plumes rise hundreds of kilometers into space, which is about 62 miles, and lava flows spread across landscapes unlike anything seen on Earth. The same gravitational interactions that warm Europa's hidden ocean also keep Io's interior in constant turmoil. These neighboring moons teach us an important lesson. A world does not require strong sunlight alone to remain active. Internal energy supplied by gravitational flexing can sustain oceans, fuel volcanism, and reshape landscapes for immense spans of time. But our present technology cannot directly detect comparable moons orbiting planets around distant stars. They remain too small and too close to their host planets for current observations to separate them clearly. Even so, the underlying physics should operate throughout the galaxy. Wherever a giant planet circles within or near a habitable region, its moons could experience tidal heating capable of sustaining subsurface oceans regardless of their distance from the parent star. A possible exomoon candidate, known as Kepler 1625 bi, has been reported from unusual transit observations, although the evidence remains disputed. Sometimes the greatest scientific prize may be circling unnoticed around the object we discovered first. Some worlds seem to erase the familiar boundaries between planets and stars. As our journey carries us farther from ordinary expectations, we arrive at Kelt 9b, a confirmed giant planet discovered during the Kilodegree Extremely Little Telescope survey in 2016. It lies about 670 light years away in the constellation Cygnus, occupying one of the most extreme environments ever measured around another star. Its dayside reaches roughly 4,300 degrees Celsius or 7,772 degrees Fahrenheit. That astonishing temperature exceeds the visible surfaces of most known stars in the Milky Way. More than 4/5 of the galaxy's documented stars are actually cooler than this single planet. You are looking at a world whose atmosphere experiences conditions normally associated with stellar surfaces rather than planetary skies. But the explanation lies in its remarkable orbit. Kelt 9b circles an exceptionally hot star whose surface reaches about 10,000 degrees Celsius or 18,032 degrees Fahrenheit. The planet completes a full orbit in only about 1½ Earth days, while remaining approximately 3 million kilometers from its star, which is about 1,864,000 miles. At that distance, the flood of ultraviolet radiation is relentless, pouring immense energy into every layer of the atmosphere. The consequences reshape the planet itself. Radiation heats the upper atmosphere until gases escape the planet's gravity, drifting outward into space. This process, known as atmospheric escape, simply means that heated particles gain enough energy to break free forever. Observations indicate that the escaping material forms a long trailing cloud, resembling the tail of a comet as the planet races around its star. Spectroscopic observations, the technique of identifying matter through its unique pattern of absorbed light, reveal an atmosphere unlike anything in our own planetary neighborhood. Iron, titanium, magnesium, chromium, scandium, yttrium, and barium all exist as gases. Temperatures remain so extraordinary that these elements cannot cool into familiar minerals or compounds. Instead, individual metal atoms drift through the atmosphere itself, creating a surrounding envelope that challenges almost every everyday idea of planetary chemistry. But the star contributes another remarkable influence. It spins with extraordinary speed, completing one full rotation in only about 16 hours. That rapid rotation helps sustain an intense output of ultraviolet radiation, continually striking the nearby planet with energetic light capable of breaking apart molecules before they can remain stable. Water, methane, and carbon dioxide cannot persist under such conditions for long. Their chemical structures are torn apart almost as quickly as they form. Astronomers estimate that Kelt 9b may survive for less than 1 billion years before continued atmospheric loss transforms it beyond recognition. By cosmic standards, that is a brief existence. We are witnessing a giant planet already dissolving under the relentless energy of its own star, reminding us that the universe sometimes creates worlds that resemble furnaces more than planets, yet they remain genuine members of the planetary family. Nothing in the galaxy remains unchanged forever. Even the stars that anchor entire planetary families eventually consume the last reserves of their hydrogen fuel and begin a profound transformation. A star like our own Sun is expected, after roughly 5 billion years, to swell into a red giant, expanding far beyond its present size. Mercury and Venus will almost certainly disappear inside that immense envelope. Earth may share the same fate. What remains afterward is a compact white dwarf, the dense core left behind after the star casts its outer layers into space. But this ending does not erase every trace of the original system. Modern observations reveal that planetary neighborhoods often continue long after the brilliant central star has faded. White dwarfs offer direct evidence that fragments of their former systems remain active, allowing us to witness the aftermath rather than merely imagine it. One of the strongest clues comes from the atmospheres of white dwarfs themselves. Their gravity is so powerful that heavier elements should sink beneath the visible surface within a few million years. Even so, astronomers repeatedly detect calcium, magnesium, iron, silicon, and other heavy elements suspended in these atmospheres. Those materials should no longer be there. Their continued presence means fresh debris is still arriving from surrounding space. The source has become increasingly clear. Asteroids, comets, and broken planetary fragments drift too close to the white dwarf and encounter tidal forces, the stretching effect created by intense gravity acting more strongly on one side than the other. These bodies are pulled apart into streams of debris before gradually falling onto the stellar remnant. The white dwarf becomes dusted with the remains of worlds that once circled a living star. But we have also witnessed destruction in real time. During the year 2020, astronomers reported observations of material actively breaking apart around the white dwarf, known as Whiskey Delta 1145 plus 017. A disintegrating planetesimal, meaning a small planetary building block, circles the remnant once every 4.5 hours while leaving behind an expanding cloud of dust. We are observing the final stages of an ancient object that survived one catastrophe only to encounter another. Evidence also suggests that larger survivors can endure. During the year 2021, astronomers announced the likely discovery of a giant planet known as Mike Oscar Alpha 2010 Bravo Lima Golf 477 Lima B, believed to orbit a white dwarf. If a planet comparable in mass to Jupiter can persist through the violent evolution of its parent star, then smaller rocky bodies may also remain scattered throughout these aged systems. Their future stretches almost beyond imagination. White dwarfs cool at an extraordinarily slow pace, requiring trillions of years before becoming theoretical black dwarfs, completely cold stellar remnants that the universe has not yet existed long enough to produce. Around those fading embers, surviving worlds may continue their endless circuits through darkness, preserving the last enduring architecture of systems whose brilliant beginnings have long since passed into cosmic history. As we widen our view beyond individual stars, another pattern gradually comes into focus. A planet may circle a suitable sun and still occupy the wrong address within its galaxy. Habitability depends on far more than the warmth of a nearby star. It also depends on the larger neighborhood through which that entire planetary system travels over billions of years. Astronomers gave this idea a formal framework during the year 2004, when Charles Lineweaver and his colleagues described what they called the galactic habitable zone. This concept proposes that only certain regions of the Milky Way combine the ingredients and long-term stability needed for complex life to emerge. The galaxy is not equally welcoming everywhere. Some regions create worlds with ease, but threaten them with frequent catastrophe. Others remain remarkably peaceful, while lacking the raw materials required to build rocky planets at all. The crowded galactic center illustrates the first problem. Stars are packed much closer together than they are in our neighborhood, increasing the likelihood of disruptive gravitational encounters. Massive stars also appear more frequently there, leading to a higher rate of supernova explosions. At the very center lies the supermassive black hole known as Sagittarius A star, surrounded by an energetic environment capable of producing intense radiation. Together, these conditions expose nearby planets to repeated bursts of ionizing radiation, meaning energetic particles and light capable of damaging living cells and altering planetary atmospheres. But traveling too far outward creates a different challenge. The outer reaches of the Milky Way contain lower metallicity, a term astronomers use to describe the abundance of elements heavier than hydrogen and helium. Iron, silicon, magnesium, and calcium are forged inside generations of stars before becoming part of new planetary systems. Where these heavier elements become scarce, the construction of rocky worlds becomes less likely. Gas giants may still form, yet Earth-like planets become increasingly uncommon. Between these extremes lies a broad ring where both requirements are reasonably satisfied. Heavy elements are plentiful enough for solid planets to assemble, while destructive stellar events occur less often, allowing biological evolution long intervals between major disruptions. This intermediate region is known as the galactic habitable zone. Our own sun resides within it, approximately 26,000 light-years from the galactic center, inside the Orion Arm, a smaller spiral arm of the Milky Way. But even this favorable location offers no complete protection. Gamma-ray bursts, the most energetic explosions known, arise when massive stars collapse or when neutron stars merge. A burst occurring within a few thousand light-years, which is about 1,900 miles, could severely damage Earth's ozone layer. Some researchers have proposed that such an event contributed to the Ordovician mass extinction about 445 million years ago, although that possibility remains under active debate. When you step back far enough, the pattern becomes unmistakable. A habitable planet requires more than a suitable orbit. It also depends on living within the rare regions of a galaxy where creation and destruction remain balanced long enough for complexity to endure. After wandering through so many astonishing planetary systems, you may notice that a different mystery begins to overshadow every discovery. The Milky Way contains hundreds of billions of stars, and many of them possess planets. Statistical reasoning suggests that intelligent civilizations should have arisen more than once. Yet every telescope still returns the same result. We see countless worlds, but no unmistakable evidence that another technological society has announced its presence. This unresolved tension is known as the Fermi paradox. It is the conflict between what probability appears to predict and what observation actually reveals. But the growing catalog of exoplanets has changed how we view that puzzle. Rather than making intelligent life seem inevitable, each newly measured world often adds another obstacle. Many planets remain permanently locked to one side of their stars. Others endure relentless radiation, lose their atmospheres, experience iron rain, or circle stellar remnants that survived violent transformations. Some wander through interstellar space without any star at all. But these discoveries also strengthen an influential idea called the Great Filter. This hypothesis suggests that somewhere between simple chemistry and a civilization capable of spreading across the galaxy lies an extraordinarily difficult step. Perhaps life rarely begins. Perhaps complex organisms seldom evolve. Perhaps technological societies usually destroy themselves or disappear before they can travel between stars. We still do not know where that barrier exists. Another possibility reaches a similar destination by examining Earth's remarkable combination of circumstances. The rare Earth hypothesis, developed by Peter Ward and Joe Kirschvink, argues that complex life required an unusual collection of favorable conditions rather than a single fortunate event. Our planet possesses a large moon that helps stabilize its axial tilt, a magnetic field generated by its molten iron core, active plate tectonics that recycle essential materials, a long-lived and comparatively stable star, and a position within a favorable region of the Milky Way. Together, these factors may represent an exceptionally uncommon combination. But another explanation asks a different question altogether. The Grabby aliens hypothesis, proposed by Robin Hansen and his colleagues, considers civilizations that expand rapidly through space. If such societies commonly arose, their presence should eventually become visible across enormous distances. We detect no such evidence. That absence could mean expansion almost never happens, or that civilizations capable of doing so have yet to appear anywhere in the observable region surrounding us. Neither conclusion offers much reassurance. If the great filter already lies behind us, then complex life may be among the rarest outcomes the universe can produce. If the filter still waits ahead, every civilization could eventually encounter the same unseen limit before leaving a lasting mark upon the galaxy. As you reflect on every extraordinary world we have visited, the enduring stillness feels less surprising. Perhaps the universe does not lack planets. Perhaps it lacks the long chain of improbable conditions required for life to survive, endure, and continue speaking across the immense gulf between the stars. Before we decide that a distant world is completely beyond hope, it helps to remember how often life on Earth has overturned our expectations. Again and again, discoveries have revealed organisms flourishing where earlier generations of scientists expected nothing could endure. Each finding has stretched the definition of habitability a little farther, encouraging us to reconsider the true resilience of biology. These remarkable organisms are known as extremophiles, meaning living things that thrive under conditions once considered fatal. They inhabit environments of crushing pressure, intense heat, extreme acidity, or relentless radiation. Their existence reminds us that the limits we imagine are often narrower than the limits nature eventually reveals. But each new discovery also teaches us where those limits finally begin to fail. Among the most astonishing examples is Pyrolobus fumarii, discovered around deep sea hydrothermal vents. This microscopic organism survives at temperatures reaching 113 degrees Celsius or 235 degrees Fahrenheit. Water remains liquid there because the immense pressure deep beneath the ocean prevents it from boiling away. Life persists, even in conditions that appear impossible from the perspective of the surface. Another extraordinary survivor is Deinococcus radiodurans. This bacterium can endure radiation doses of approximately 1,500,000 rads, then rebuild its damaged deoxyribonucleic acid through remarkably efficient repair mechanisms. For comparison, roughly 1,000 rads prove fatal for most human beings. It has even survived brief exposure to the vacuum of space during carefully controlled experiments. But perhaps the most famous champions of endurance are the tardigrades. These microscopic animals, each measuring less than 1 millimeter, which is about 0.04 inches, have survived the vacuum of space, temperatures approaching negative 272 degrees Celsius or negative 458 degrees Fahrenheit, and heat reaching 150 degrees Celsius or 302 degrees Fahrenheit. They also withstand pressures several times greater than those found in the deepest ocean trenches and radiation levels thousands of times beyond what humans can tolerate. The surprises continue beneath our own feet. Life has been discovered inside solid rock several kilometers underground, that is nearly several miles beneath the surface. Microorganisms inhabit the intensely salty waters of the Dead Sea, acidic drainage flowing from abandoned mines, Antarctic ice sheets, and even the cooling water surrounding nuclear reactors. Then, during 1977, scientists uncovered thriving hydrothermal vent ecosystems powered entirely by chemosynthesis, a process that produces biological energy from chemical reactions instead of sunlight. Entire communities of tube worms, crabs, and bacteria flourished in complete darkness. But these discoveries answer only part of the larger question. They demonstrate that life, once established, possesses astonishing endurance. They do not prove that life can originate under every extreme condition. A world where iron falls as rain at approximately 2,400 degrees Celsius or 4,352 degrees Fahrenheit destroys the molecular structures upon which biology depends before they can organize into living systems. Our understanding of life's boundaries has expanded dramatically, yet the harshest worlds we have explored still remain beyond even those extraordinary limits. Looking back across the extraordinary worlds we have explored, a remarkable pattern begins to emerge. The universe has discovered countless ways to assemble planets, yet very few resemble the one beneath our feet. Each hostile landscape reveals another path that planetary evolution can follow, reminding us that familiar conditions are far from inevitable. You begin to see Earth less as a standard outcome and more as an uncommon destination. Our world circles a stable Group G star, a stellar class representing only about 7% of the stars within the Milky Way. Such stars shine steadily for billions of years, providing long periods during which life can emerge and evolve. Many stars are far more active, while others emit much less energy. But our Sun occupies a range that has proven remarkably favorable for maintaining liquid water across immense stretches of time. Earth also possesses an unusually large moon, born from an ancient giant impact during the earliest history of the solar system. That dramatic collision left behind a companion whose gravity stabilizes Earth's axial tilt to approximately 2.4 degrees over immense timescales. Without that stabilizing influence, calculations suggest the planet's tilt could wander between 0 degrees and 85 degrees. Such enormous shifts would transform climates repeatedly, placing lasting pressure on stable ecosystems. Another uncommon advantage lies beneath the continents and oceans. Earth experiences plate tectonics, the slow movement of enormous rocky plates across the planet's surface. This geological engine continually recycles carbon dioxide between the atmosphere and the mantle, creating a natural thermostat that has helped maintain temperatures suitable for liquid water for more than 3 billion years. But neither Venus nor Mars appears to sustain active plate tectonics today. Deep inside the planet, molten iron circulates through the outer core and generates a powerful magnetic field. This invisible shield deflects much of the charged particle stream flowing outward from the Sun, helping preserve the atmosphere across billions of years. Without such protection, atmospheric gases could gradually escape into space, reshaping the surface environment over geological time. Far beyond Earth's orbit, Jupiter contributes another piece of this intricate arrangement. Its immense gravity alters the paths of many long-period comets before they enter the inner solar system. The relationship is more complicated than once believed, and Jupiter can also redirect some objects inward. But overall, its presence influences the impact history experienced by the inner planets. Our oceans complete another remarkable combination. Covering approximately 71% of Earth's surface, they moderate temperatures, dissolve atmospheric gases, support complex chemistry, and transport heat through powerful global currents. Each of these processes helps create environmental stability that living systems can exploit across immense spans of time. None of these characteristics was guaranteed. Every one emerged from a chain of contingent events involving planetary formation, stellar evolution, galactic location, and extraordinary timing. Today, the catalog of confirmed exoplanets contains more than 5,600 worlds, yet none has been confirmed to match Earth's size, composition, orbit, and stellar environment all at once. We are discovering many planets, but we are still searching for another world that truly feels like home. Imagine returning to every extraordinary world we have visited after unimaginable spans of time. None would appear exactly as we left it. Planetary systems evolve without pause, shaped by gravity, radiation, collisions, and the slow aging of stars. Even the most violent landscapes are temporary. Given enough time, every orbit changes, every atmosphere transforms, and every planet ultimately reaches an ending written into the physics that created it. One of the shortest futures belongs to WASP 12b. This swollen giant continues spiraling toward its host star, its outer atmosphere steadily pulled away by overwhelming tidal forces. Astronomers estimate that within roughly 10 million years, an instant on geological timescales, the planet will cross the final boundary and disappear into the stellar surface. Its story ends with complete destruction. But other worlds fade more gradually. Kelt 9b is steadily surrendering its atmosphere to relentless stellar radiation. Powerful streams of gas escape into space, forming an enormous trailing cloud that follows the planet along its orbit. Over approximately 1 billion years, continued evaporation may strip away the outer layers until only a dense, rocky, or metallic core remains. The giant planet we recognize today could become something entirely different. WASP 76 B faces a similar destiny. Its orbit slowly decays as tidal interactions exchange energy between the planet and its star. As that inward migration continues, the forces shaping its remarkable weather patterns will eventually give way to complete engulfment. The famous iron rain cannot fall forever. Even the most astonishing climate has a finite lifetime. Far beyond these dramatic endings, white dwarf systems settle into astonishingly long periods of decline. Their surviving asteroids, planetary fragments, and distant worlds continue circling stellar remnants that cool for trillions of years. Each passing era leaves the central object dimmer than before until it radiates almost no remaining warmth. But the planets continue their lonely revolutions through an increasingly dark environment. Rogue planets experience a different future altogether. Having escaped the gravity of any star, they drift through interstellar space for billions upon billions of years. Their interiors gradually lose stored heat while their surfaces cool until they approach the temperature of the surrounding universe. Eventually, there is little distinction between the frozen planet and the darkness surrounding it. Stretch your imagination even farther. Stars eventually exhaust their fuel. New stellar births become increasingly rare. Galaxies themselves grow darker across incomprehensible expanses of time. Some theoretical models even suggest that protons, the particles forming ordinary matter, may ultimately decay, although no experiment has yet confirmed that possibility. If that process truly occurs, even the most durable planetary materials would eventually disappear. But long before those remote epochs arrive, every world in this catalog will already have surrendered its present identity. Storms will cease, atmospheres will vanish, mountains will erode beneath unfamiliar forces. Gravity assembles remarkable worlds with extraordinary patience, yet the universe displays equal patience while reclaiming them. What seems permanent during a human lifetime is simply another passing chapter in a cosmos that never stops changing. Stand for a moment at the edge of everything we currently know, and you discover something unexpected. The map itself reveals where our vision fades. Every confirmed planet enriches our understanding, yet every discovery also outlines a larger territory that remains beyond today's instruments. We have learned an astonishing amount, but the catalog is shaped as much by technological limits as by the universe itself. More than 5,600 confirmed exoplanets now fill astronomical databases, each adding another point to an expanding portrait of planetary diversity. But this remarkable collection carries a profound selection bias, meaning the sample is influenced by how observations are made rather than by what truly exists. Large planets, crossing the faces of their stars, create deeper dimming, making them easier to detect. Massive worlds also tug more strongly on their stars, producing clearer signals through the radial velocity method, which measures tiny stellar motions caused by orbiting planets. Bright nearby stars help as well. Their light provides cleaner measurements, while planets circling close to them complete frequent orbits that offer repeated opportunities for confirmation. But the worlds most resembling our own are far less cooperative. Small, rocky planets, traveling around sun like stars at Earth, like distances, produce only the faintest signatures. Their transits occur infrequently, sometimes only once each year, demanding extraordinary patience and precision from observers. That challenge explains why a genuine Earth analog remains unconfirmed. Astronomers define such a world as one matching Earth's size, rocky composition, orbital distance, and stellar environment. Detecting the tiny decrease in starlight produced by such a planet pushes existing instruments to their practical limits. Measuring the subtle gravitational pull from that same world proves equally demanding. Studying atmospheres raises the difficulty even further. The James Webb Space Telescope has transformed atmospheric science by examining large, hot planets that transit often and generate comparatively strong signals. But habitable rocky planets produce atmospheric fingerprints that are far weaker. Their rare transits provide fewer opportunities, while the thin layers of gas surrounding them leave only delicate traces within the starlight passing through. But future observatories promise to broaden that view. The Nancy Grace Roman Space Telescope is expected to search for colder planets through gravitational microlensing, a technique using the gravity of foreground stars to magnify distant starlight and reveal otherwise hidden worlds in wide orbits. Another ambitious proposal, the Large Interferometer for Exoplanets mission concept, seeks to combine multiple space telescopes into a single infrared observatory capable of directly imaging nearby Earth-sized planets. As of the middle of the present decade, that mission remains under development rather than approved for flight. Even with these advances, one central question remains unanswered. How common are planetary systems arranged like our own, with inner rocky planets, distant gas giants, and long-term orbital stability? Current observations cannot answer with statistical confidence because the easiest planets to detect are rarely the most ordinary ones. But that limitation carries its own reminder. The loudest planetary voices reached us first because they were easiest to hear. The quieter worlds still wait beyond today's horizon, and history suggests they may reshape everything we believe we know. Every discovery we have explored began as an almost impossible act of patience. Before a distant planet could become a place with weather, chemistry, or history, someone first imagined that such details might be measurable at all. You and we inherit the results of countless observations made across generations, each one adding another piece to a picture far larger than any single lifetime. The iron rain identified on WASP 76b emerged through years of careful work using the Echelle spectrograph for rocky exoplanets and stable spectroscopic observations, an instrument engineered with extraordinary precision. Spectroscopy, the study of how matter absorbs and emits light, allowed astronomers to separate starlight into its component colors and detect tiny shifts caused by iron vapor moving at several kilometers per second, which is about several miles per second, through the planet's atmosphere. Those minute changes revealed winds that no telescope could ever photograph directly. But that achievement was only one chapter. The first confirmed detection of atmospheric carbon dioxide on WASP 39b required the James Webb Space Telescope, itself the culmination of more than 25 years of planning, construction, testing, and collaboration. Thousands of scientists, engineers, technicians, and support, specialists representing 14 countries, contributed to a single observatory capable of measuring the faint chemical fingerprints carried within distant starlight. A molecule became visible because generations refused to abandon an ambitious idea. Earlier still, another remarkable discovery arrived through a completely different path. The planets orbiting the pulsar, designated Pulsar B, 125, 7 plus 12, were uncovered by a radio astronomer, studying tiny irregularities in repeating pulses arriving from deep space. Those signals resembled steady cosmic clocks, yet careful mathematics revealed subtle variations caused by unseen planetary companions tugging on the pulsar itself. Years of disciplined observation transformed timing noise into the first confirmed planets discovered beyond our own planetary system. Consider what that truly means. The light carrying evidence of iron rain from WASP 76b has traveled for approximately 640 light years before reaching Earth. It began its journey roughly 640 years ago, during the early Renaissance, before Christopher Columbus crossed the Atlantic Ocean and before the printing press had spread widely across Europe. We observe ancient light while constructing a present-day map of the universe. But those distant worlds never depended on our awareness. Their storms unfolded without witnesses, their atmospheres changed without applause, their stars continued shining, whether anyone measured them or not. Nature does not pause for observation. Still, something remarkable happened here. On a rocky planet, orbiting an ordinary star within a minor spiral arm of the Milky Way, living beings assembled mirrors, detectors, equations, and computers capable of reading the chemistry of a world separated by unimaginable distance. The atoms inside our bodies were forged in ancient stars, and those same atoms eventually learned to study other stars and the planets circling them. Across the vastness between worlds, the universe became aware of one small part of itself. That alone reshapes the scale of the human story. As our journey comes to rest, the countless worlds we have visited begin to settle into a single thought. The word terrifying has followed us from one discovery to the next, and it remains the right word. These planets are terrifying, not because they threaten us personally, but because they reveal a universe whose scale and violence reach far beyond anything human experience was shaped to understand. The universe does not choose kindness or cruelty. It follows the laws of physics with unwavering consistency, allowing every possible outcome those laws permit. From that process emerge iron rain, continents of molten rock, storms filled with shattered glass, planets whose temperatures exceed those of many stars, frozen wanderers crossing interstellar darkness alone, and ancient worlds circling the fading embers of dead suns. None of these places exist to inspire fear. They simply exist. But if you remain with that realization long enough, its meaning begins to change. The overwhelming vastness stops feeling like a threat and starts becoming a measure of perspective. Against such an immense background, the familiar conditions of our own world become increasingly extraordinary. Earth was never the default destination for planetary evolution. It became one remarkable outcome within an almost limitless range of possibilities. Our planet orbits a stable star, carries liquid water across much of its surface, preserves an atmosphere through a lasting magnetic field, and has sustained conditions favorable for life across billions of years. From that rare combination, chemistry gradually organized into living cells. Cells became organisms. Organisms reshaped oceans and continents. Eventually, one branch of life learned mathematics, built telescopes, and deciphered the faint fingerprints hidden within starlight that had traveled across hundreds of light years. Think about that distance once more. The light revealing iron rain on WASP 76b began its journey approximately 640 light years away. It crossed empty space for roughly 640 years before reaching mirrors and detectors built by curious minds on Earth. We observed an ancient moment while standing firmly in the present. Across that unimaginable gulf, understanding became possible. Many years ago, Carl Sagan described Earth as a pale blue dot, a mote of dust suspended in a sunbeam. That image remains as powerful today as when he first shared it. But the growing catalog of more than 5,600 confirmed exoplanets adds another layer to that vision. We now know that countless other motes exist, each shaped by different histories, different environments, and different outcomes. Very few resemble home. The darkness beyond our skies is real. Those distant storms continue without witnesses. Their atmospheres shift, their mountains melt, their frozen surfaces drift through endless night. The universe carries on, whether we observe it or not. But here, on one improbable world, during one brief moment in cosmic history, something looked upward and wanted to understand. That desire may be the rarest phenomenon we have encountered. Sleep now. The universe is vast, ancient, and waiting, and it will still be there when morning comes.